Assalamu alaikum wa rahmatullahi wa barakatuhu. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi yassir wa la tu'assir wa tammim bil khair. So in this video we will continue our topic of DC machinery, DC machine fundamentals. So in the previous video we have seen that how the voltage is induced and how the torque is produced in the simple loop machine, DC machine. And we have applied the commutators to this machine so that we can have the DC or direct voltage, one-sided voltage that can be produced even if it is a generator, or we can apply a DC voltage to the motor. So let's look at some problems that are related with this commutation in real machines. So there are actually two basic problems that actually affect the machine performance and machine working. One is known as the armature reaction, and the second one is known as the LDI by dt voltages. So armature reaction, so let's look at armature reaction. Armature reaction is once already we have seen in the synchronous machines, and we have said that when the main field that induces the voltage into the armature, so that armature will have its own current, and that will also produce another magnetic field that will distort the original magnetic field of the field winding of the field, so that interaction of those two fields actually causes the problem. So that's known as the armature reaction. So here we have the same phenomena. If the magnetic field windings of the DC machine are connected to the power supply and the rotor of the machine is turned by external source of mechanical power, then a voltage will be induced in the conductors of the rotor. This voltage will be rectified into a DC output by the action of machine's commutator. Now connect a load to the terminals of the machine, and the current will flow in its armature winding. This current will produce a magnetic field of its own, which will distort the original magnetic field from the machine's pole. So this distortion of flux in a machine as the load is increased is called armature reaction. So the effect of two fields that actually causes some problem there, so that is called the armature reaction. So what happens with this armature reaction? So armature reaction again causes two serious problems in real DC machines. One problem is the neutral plane shift. So neutral plane shift actually is defined as the plane within the machine where velocity of the rotor wires is exactly parallel to the magnetic flux lines. Here we can see, so magnetic flux line will be here straight, means obviously it will be like this and going from here to and then straight. So where the velocity of the rotor wire is exactly parallel to the magnetic flux lines. So at this point, so that the E induced, the voltage induced in the conductors in the plane is exactly zero. So at this point there will be no induced voltage. Here we can see that there is no dot or cross here, so it shows that there is no voltage induced in this portion. So this figure A shows a two-pole machine. Notice that the flux is distributed uniformly under pole faces. As we know that this flux in this is uniformly distributed in the air gap. So the rotor windings shown have voltages built up out of the page for wires under the north pole and into the page for the wires under the south pole face. So the neutral plane in this machine is exactly vertical. So now suppose a load is connected to this machine so that it acts as a generator. So obviously the current will flow out of the positive terminal here of the generator, so the current will be flowing out of the page for wires under the north pole and into the page for wires under the south pole face. This current flow produces a magnetic field from the rotor windings. So rotor windings will now again produce this magnetic field, where we have this uniform magnetic field, which is not shown here in this figure, but we have this uniform magnetic field that is we have seen here, that is coming perpendicular to this rotor. So the rotor magnetic field effects, here we have shown both of the fields, which this is from the field winding, or the field from the field which is produced by the north and south permanent magnet poles, And if we have connected a load and we are suppose using this machine as the generator, so it will produce a magnetic field of its own in the rotor. So here what will happen when we load it, the original magnetic field from the poles that produce the generator's voltage in the first place. In some places under the pole surfaces, it subtracts from the pole flux. Somewhere here it will be subtracting, and here it will be obviously adding and in other places it adds up to the pole flux. The overall result is that the magnetic flux in the air gap of the machine is skewed. So this magnetic flux is skewed. Here we can see here. So here we can see that this magnetic flux is now means somewhere here it is stronger and somewhere it is weaker now. So notice that the place on the rotor where the induced voltage in the conductor would be 0, the neutral plane has shifted. So what happens due to this stronger field and this weaker field? So this neutral plane will shift in the direction of the rotation of this generator. So where we have these shifted our neutral plane. So here we can see that our neutral plane is shifted here. So for generator shown here, the magnetic neutral plane shifted in the direction of rotation. So if this machine had been a motor, the current in this rotor would be reversed. Obviously, if this is a motor, so current will be in opposite direction because we are supplying it. So the current in this rotor would be reversed and the flux would bunch up in opposite corners. Means this bunching here, we can see here, this is the bunching here. So that will be in opposite corners here in machine if it is used as the motor. So this bunching will shift the neutral plane in opposite direction like here. So as a result, the magnetic neutral plane would shift to the other way. So in general, the neutral plane shifts in the direction of motion for generator and opposite to the direction of motion for a motor. So furthermore, the amount of shift depends on the amount of rotor current and hence on the load of the machine. Means how much load we have and how much current is flowing. Based on that, we will have that much stronger flux in this rotor, and that will make stronger bunch here and more weaker field here. So that neutral plane shift will depend, how much it will shift will depend upon the current and the flux that is producing this rotor. So what is so important regarding the neutral plane shift? So the commutator must short out commutator segments just at the moment when the voltage across them is equal to 0. Means when they are on the neutral plane. So if the brushes are set to short out conductors in a vertical plane, then the voltage between segments is indeed 0 until the machine is loaded. So when the machine is loaded, the neutral plane shifts and the brushes short out commutator segments with a finite voltage across them. So the result is a current flow circulating between the shorted segments and the large sparks at the brushes when the current path is interrupted as the brush leaves a segment. So the end result is arcing and sparking at the brushes. So this is the basically the one of the biggest issue that happens in these machines, and that actually decreases the life of the machine, and we have to service the machine more often. So this is a very serious problem since it leads to drastically reduced brush life. So obviously when the brushes are finished and also they will produce some powder like things in the machine, so that will actually we have to clean it, we have to clean this machine more often. So pitting of the commutator segments and higher maintenance costs. So notice that this problem cannot be fixed even by placing the brushes over the full load neutral plane, because then they would spark at no load. So this is one of the big problem. So in extreme cases, the neutral plane shift can even lead to a flashover in the commutator segments near the brushes. So the air, what is flashover, what happens? The air near the brushes in the machine is normally ionized as a result of the sparking on the brushes. So flashover occurs when the voltage of adjacent commutator segments gets large enough to sustain an arc in the ionized air above them. So if flashover occurs, the resulting arc can even melt the commutator surface because it's a continuous arc. Sometimes we we can see these types of arcs on the transformers when we have the loose connections there. So sometimes we can see those arcs obviously produced there. So this is actually I have sum up all the figures here. So this is normally when there is no load on the machine, and we have this uniform magnetic field in the air gap. But and this is how these magnetic flux of lines will flow from north to south poles. So they because they have to shift into the perpendicular direction because of the high reluctance of the air. So when we load them, there will be a magnetic field of the rotor itself, and that will actually create the bunching here that we can see here. So that bunching will actually shift the neutral phase, a new neutral plane. So obviously if it is used as the generator, it will be in the direction of the rotation, but if it is a motor, it will be opposite to the direction of the motion because of this bunching. Just remember this bunching here, and this is means the field is strong. Field becomes stronger here because they are adding here. You can see because they are adding here, they are in the same direction. Here it is in the opposite direction, so they will cancel out some of the field, and that will be added together at these points. So here it will be cancelled out here, and it will be added here. So it will become stronger here and stronger here, and weaker here and weaker here. So that will shift this neutral plane. So second problem with this commutation is due to the armature reaction is flux weakening. So the second major problem caused by the armature reaction is called flux weakening. So most machines operate at flux densities near the saturation point. So therefore, at locations on the pole surfaces where the rotor magnetomotive force adds to the pole magnetomotive force, only a small increase in flux occurs. So, but at locations on the pole surfaces where the rotor magnetomotive force subtracts from the pole magnetomotive force, there is a larger decrease in flux. So, the net result is that the total average flux under the entire pole face is decreased. So, flux weakening causes problems in both generators and motors. In generators, the effect of flux weakening is simply to reduce the voltage supplied by the generator for any given load. So in motor, the effect can be more serious. As the flux in the motor is decreased, its speed increases. So, but increasing the speed of the motor can increase its load, resulting in more flux weakening. It's possible for some shunt DC motors to reach a runaway condition as a result of the flux weakening, where the speed of the motor just keeps increasing until the machine is disconnected from the power line or until it destroys itself. So here we can see so this is a magnetizing curve, and we can see the same problem here. So because we know that the most of the machines operate at flux densities near the saturation point, so yeah, so at locations on the pole surfaces where the rotor magnetomotive force adds to the pole magnetomotive force, only a small increase in flux, only a small increase in flux densities near the saturation. So the locations at the pole surfaces where the rotor magnetic force adds to the pole magnetomotive force, only a small increase in flux occurs. But at locations on the pole surfaces where the rotor magnetomotive force subtracts from the pole magnetomotive force, there is a larger decrease in flux. So the net result is that the total average flux under the entire pole face is decreased. So we have seen that because of this flux weakening problem in generator, the output voltage will be reduced. But what happens into the machines that it actually increases the speed of the rotor beyond the rated speed. Sometimes it's not a big problem because we use this flux weakening technique to control the speed of the motors. Means if you want to go beyond the rated speed, we can reduce the field by ourselves by using some techniques, and we can go beyond the rated speed. But just like we have seen that in the DC shunt motors, this could happen. If this things happens in that motor, it can actually may destroy the DC machines. So the second problem with the commutation, which is LDI by dt, we will look into the next video. So I hope you have understood so far. Still, if you have any question, please feel free to ask. Assalamu alaikum wa rahmatullahi wa